last couple of lectures, I have worked out a series of exercises for you pertaining to operator algebras and uncertainty relations and so on. Today I will continue to work out some more exercise problems. These will be problems of direct relevance to various physical situations, and therefore I will explain the importance of the problems that I will attempt to work out as I go along. So again we have exercises. The first exercise pertains to the harmonic oscillator, the linear harmonic oscillator, for which if I set m equals omega equals h cross equals 1 for simplicity, I can always put them back later once I do the calculation, then x would simply be a plus a dagger by root 2 and p would be a minus a dagger by root 2 I, and of course the commutator xp is I times the identity operator. I have set h cross equals 1. This would also correspond to a dagger equals 1, the identity operator again. So I will work with this example where m is equal to omega equals h cross equals 1, and what I will attempt to find out are the following: expectation value of x in any state n of the oscillator, expectation value of p in any state n of the oscillator. Recall that n takes values 0, 1, 2 and so on. N equals 0 is the ground state of the oscillator. Then we can build up the excited states from the ground state. We also want to know what is the expectation value of xp plus px in the state n. So that would be the first problem that I will attempt. I wish to calculate these three objects. So let us start with the expectation x. This is identical to n x n, and that is equals 1 by root 2 n a plus a dagger n. That is simply n a n plus the expectation value of a dagger in the state n. A n takes this apart from some coefficient to the state n minus 1, and a dagger takes this apart from a coefficient to the state n plus 1, but the states are orthonormal to each other, they are orthogonal to each other, and therefore this would simply be n n minus 1 apart from this coefficient, therefore this is 0. Similarly, this would be n n plus 1, and that is also 0, and therefore the expectation value of x in any state of the harmonic oscillator, by state I mean one of the natural basis states in that linear vector space or the Fock states. In quantum optics language you would refer to them as the photon number states and x as a quadrature variable. So expectation x is 0. Now suppose I wish to find out expectation p in any of these states. I would repeat this, substituting p is a minus a dagger by root 2 I. So I wish to find this is identical to expectation p, and that is given by 1 by root 2 a minus a dagger. There is also an I n. Once more I use the same argument. A acts on n to lower it to n minus 1, but ket n is orthogonal to ket n minus 1. Similarly, a dagger raises this to n plus 1, and the second term also is 0, I use the same arguments as I used earlier, and therefore expectation value of P is 0. This can be explained well when one goes to the position representation and the momentum representation, which I will subsequently. It has to do with the fact that all the energy eigenstates, when written as functions of x, when written as wave functions, that is functions of x, they have a definite parity. It is rather early in the day to discuss that, but I will come back to this problem when I discuss the harmonic oscillator in the position representation later on. The next thing I wish to prove is that this object is also equal to 0. So, let me work that out. So, we start with n xp plus px n, but we know that the commutator of x with p is I, therefore, xp is I plus px. Actually, it is I h cross times the identity operator out there, but we have set h cross equals 1. So, xp is simply I plus px, and therefore, I can write this as I plus 2 px, and I want the expectation value in the state n. The first term simply gives me I. The second term is really this. I now expand P and X in terms of A's and A daggers. Px is A minus A dagger by root 2 I times A plus A dagger by root 2. This object is half I A squared minus A dagger squared plus A dagger minus A dagger A. I use this and I find out expectation xp plus px. So, I get expectation xp plus px in the state n is I plus 1 by 2 I expectation A squared, that is a minus A dagger squared, plus A dagger minus A dagger A in the state n. If you look at the first term, when A squared acts on ket n, well, the first time around A reduces n to n minus 1, then the second time it reduces n minus 1 to n minus 2. So, when A squared acts on ket n, I get ket n minus 2, and again ket n is orthogonal to ket n minus 2. So, this term does not contribute. So, this expectation value is 0. Similarly, A dagger square's expectation value is 0. What I would be left with would be objects like this. So, this is I minus I by 2 expectation value of n A dagger minus A dagger A n. But I can always use the fact that A dagger is 1 plus A dagger A. I have xp plus px, and this gave me a 2 px. So, there was already a 2 outside, and therefore, I need to put in xp plus px, I need to put a 2 there, So, the 2's cancel and I am left with I minus I, because the inner product of n with n, bra n with ket n is 1, and therefore, the answer is 0. So, you see the expectation value in any state n of the oscillator of the object xp plus px, that operator xp plus px is 0. So, what we have established in the first exercise is that expectation x, expectation p and expectation xp plus px all vanish in any state of the oscillator. I now move on to the next exercise. To find out delta x and delta p in any state n of the oscillator. We have already shown that delta x, delta p take on minimum values in the ground state of the oscillator, and if I set h cross equals 1, delta x is 1 by root 2 and delta p is also 1 by root 2, and therefore, the product delta x delta p takes its minimum value, which is half. So, now in any state of the oscillator, I wish to find out delta x delta p. Recall that delta x squared is expectation x squared minus expectation x the whole squared, but we have just shown that expectation x is 0 in any state of the oscillator. So, I need to calculate expectation x squared. X squared in units where m, omega and h cross are 1 is simply a plus a dagger the whole squared by 2, which is a half a squared plus a dagger a plus a dagger plus a dagger squared. So, if I need to find the expectation value of x squared in the state n, I need to calculate the expectation value of these 4 objects when sandwiched between ket n and bra n. Look at the first term. As I argued before, this will not make a contribution, the last term will not make a contribution. So, I have half a dagger a plus a dagger, the expectation value of just this operator. Once more, I can write a dagger as 1 plus a dagger a, and I need to compute this. I have used the fact that a dagger is 1 plus a dagger a, and that is why I got that. The first term just gives me a half. The second term gives me, there was a 2 from here and a 2 from there, so that cancels out. It gives me n, and therefore, I get n plus half. So, delta x the whole squared is n plus half in the state n of the oscillator. And that is why in the ground state, delta x in the ground state is just the positive square root of n plus half, and that is why in the ground state of the oscillator delta x was 1 by root 2, I have set h cross equals 1, you could put it back and then you will have root of h cross by 2. In any other state, delta x is root of n plus half. So, in the first excited state, delta x is equal to root of 3 by 2, again in units of h cross equals 1, and therefore, if I put back the h cross, it is root of 3 h cross by 2, and so on. So, you have the ground state which is a minimum uncertainty, and delta x keeps increasing as the state label increases. Now, let us look at delta p. Once more I use the same procedure. Delta p the whole squared is expectation p squared minus expectation p the whole squared. We have just shown that this object is 0 in any state n of the oscillator, and therefore, I need to compute expectation p squared. P squared is a minus a dagger by I root 2, a minus a dagger by I root 2. And this object is a minus half a minus a dagger times a minus a dagger. So, I can expand it and write it in this manner. I need to find n p squared n, and that is minus half expectation a squared minus expectation a dagger a minus expectation a dagger plus expectation a dagger squared, all expectation values obtained in the state n. As before, this is 0 and so is this. I need to only worry about the contributions from a dagger a and a dagger. So, n p squared n is half a dagger a plus a dagger. But this is precisely what we computed earlier, and this will give me an answer n plus half, because once again I will write a dagger as 1 plus a dagger a. Therefore, delta p the whole squared is n plus half. Of course, if I put in the h cross, I get this, and therefore, delta p is square root of n plus half, the positive square root. While in the ground state, I have the minimum value. In the first excited state, it is 3 h cross by 2, the square root of 3 h cross by 2, and so on, and we find that delta x is equal to delta p in any state ket n of the oscillator. So, this is what the first exercise was about, and we have established that while the ground state is a minimum uncertainty state, in all other states delta x and delta p do not vanish, because expectation x squared and expectation p squared are non-zero, but we have shown explicitly that delta x equals delta p, and the uncertainty product gets larger and larger as we go to higher values of n. My next exercise concerns the qubit. I now wish to look at the state psi which is ket 0 plus e to the I theta ket 1, where theta is e to the I theta is just a phase. It is normalized, I can check that out, it is normalized to unity because this object is 1 and so is this, and therefore, I take this normalized state ket psi, it is a qubit, it is a superposition of ket 0 and ket 1, and I wish to find expectation x and expectation p in the state psi. So, expectation x in the state psi implies computing this I have set m equals omega equals h cross equals 1. But that object is the same as 1 by root 2 bra 0 plus e to the minus I theta bra 1 by root 2 a plus a dagger ket 0 plus e to the I theta ket 1 by root 2. And that gives me 1 by 2 root 2 and I have to compute this. So, this is what I have. This involves the following terms. First I have 0 a 0, then I have 0 a e to the I theta ket 1 that is what I have worked with first. Then I have 0 a dagger 0 plus e to the I theta 0 a dagger ket 1. Now, I move to the second term here. So, that gives me plus e to the minus I theta 1 a 0. There is an e to the minus I theta times e to the I theta. So, I just have 1 a 1. I work with the dagger now. So, that gives me an e to the minus I theta 1 a dagger 0 and the last term which is simply 1 a dagger 1. This is what I need to compute. It is clear that this is 0 because a on ket 0 is 0. This will make a contribution because a on ket 1 is ket 0 and therefore, this object simply turns out to be e to the I theta. A dagger on ket 0 is ket 1 and by the fact that ket 0 and ket 1 are orthogonal, that is 0. This is ket 2 and I have a 0 here. So, this is also 0. This annihilates the vacuum or the ground state and therefore, it is 0. This brings it down to the ground state and because ket 1 and ket 0 are orthogonal, this is 0. This contributes because a dagger on ket 0 is root 1 ket 1. So, this whole term is simply e to the minus I theta. This is 0 because this takes it to ket 2 and ket 1 and ket 2 are orthogonal to each other. So, I have psi x psi where psi is the qubit that I have selected. This object is 1 by 2 root 2 e to the I theta plus e to the minus I theta and that is what I have. There was an e to the I theta here and there was an e to the minus I theta there. The whole thing is multiplied by 1 by 2 root 2. So, this is just cos theta by root 2. What about psi p psi? I can repeat this argument and expand putting in the appropriate values, the appropriate operators for p. I leave that as an exercise. That is again non-zero. So, here is a state where expectation x is not 0 and expectation p is not 0. Again, as an exercise, one can compute delta x and delta p in this state. They are not minimum uncertainty superpositions of 0 and 1. The uncertainty product is higher than what you would expect for the ground state of the oscillator. Calculations like this, exercises like this would become relevant in quantum computation, where qubits are used and expectation values of various operators in a qubit state become important. My next exercise is to compute the expectation value of x in a very interesting state. I define that state as a dagger acting on ket alpha. I have to normalize this, where ket alpha is the standard coherent state. And as you know, this is an eigenstate of A with eigenvalue alpha, alpha being a complex number. Now, first of all, let us normalize that state. So, consider this object. I can always write this in terms of A dagger A. The idea is to get A to this side, because then I know that I can use this property and therefore this property. So, A dagger is 1 plus A dagger A, and I need to find this, but this is something I know. The first term is simply 1, because alpha is a normalized state, normalized to 1, plus mod alpha squared. That comes from the expectation value of A dagger A in the state alpha. So, this object is just 1 plus mod alpha squared, and therefore, the state psi, which is 1 by root of 1 plus mod alpha squared A dagger on ket alpha, this state you can easily check is a normalized state. Now, in the parlance of quantum optics, what is it that I have done? Taken the standard coherent state of light, acted once with the photon creation operator. So, this is a photon added coherent state, suitably normalized, or the single photon added state, coherent state. Now, I want to calculate expectation x in this state. This is what I wish to find. But x itself is A plus A dagger by root 2, and therefore, the expectation value of x in this state is 1 by root 2 I have just taken the bra psi. Of course, there is going to be a normalization, and that is 1 plus mod alpha squared. So, a 1 by root 2 that came from x and a 1 plus mod alpha squared that comes from the normalization of the state, A plus A dagger on ket alpha. So, this is what I have. Now, that is just 1 by root 2 mod 1 plus mod alpha squared. I have two terms here. The first is the expectation value of A squared A dagger in the state alpha. The next is the expectation value of A dagger squared in that state. Now, it is clear that this operator here, its dagger is here, and therefore, if I know this expectation value, I can always take the complex conjugate and get the other expectation value. So, I have 1 by root 2 1 plus mod alpha squared. Look at this. Once more, it is good to shift A to that side. So, I have A times A dagger, which is 1 plus A dagger A. So, I have just written this operator out here plus this operator. So, this number is the complex conjugate of that number. And what do I get here? That is 1 by root 2 1 plus mod alpha squared. The first term is just the expectation value of A in the state alpha, and that just pulls out an alpha because of this property. The next is expectation value of A dagger. This A acting on alpha pulls out an alpha. So, that is what I have. By this, I mean just take down this term and put it there. Again, I write A dagger as 1 plus A dagger A. And now I know what is happening. This expectation value therefore becomes 1 by root 2 1 plus mod alpha squared. The first term gave me an alpha, and here there is already an alpha. So, I just have to look at this operator and what it gives me. So, the first term gives me an alpha times a 1 plus mod alpha squared. And so, I have alpha from the first term plus alpha times 1 plus mod alpha squared, and then of course, its complex conjugate that came from the second term. So, basically I can now simplify and write this as 2 alpha plus alpha mod alpha squared, and from there 2 alpha star plus alpha star mod alpha squared. This can be further simplified. I leave it to you to put this in a better form and realize that A dagger on ket alpha, the single photon added coherent state, is a very important state because first of all, it has been produced in the laboratory about 5 years ago, and it is not a perfect coherent state, but it departs from coherence quantifiably, added 1 photon to the coherent state, and to that extent created a departure from the coherent state. Now, I could have in general created an M photon added coherent state in principle, and that is got by repeated application of A dagger M times on ket alpha, suitably normalized. This is the normalization constant. And I would call this state the M photon added coherent state. Such states become very important in various contexts. I now move on to a nonlinear Hermitian operator, which is nonlinear in A and A dagger. Consider the operator A dagger squared A squared. I have very deliberately used H there, because if I put in some overall constants outside, I find that this Hamiltonian is the effective Hamiltonian for nonlinear optical medium specifically the Kerr medium. This is the effective Hamiltonian. For a Kerr medium or a nonlinear optical medium. I wish to find out the eigenspectrum of this Hamiltonian. So, let me proceed to work out that exercise. I consider A dagger squared A squared. I can write this the idea is to write it as A dagger A dagger A. So, I write A dagger A in terms of A dagger. Recall that A dagger is 1 and therefore, A dagger is 1 plus A dagger A. So, I can write A dagger A as A dagger minus 1 and there is an A there. So, this object is simply A dagger A minus A dagger A. In other words, in terms of the photon number operator n, this is n squared minus n or n into n minus 1, where n is the photon number operator. I therefore need to find out the eigenvalues and eigenfunctions of this Hamiltonian h cross chi n times n minus 1. It is evident that the basis set ket n, the n photon state for instance, is an eigenstate of this Hamiltonian, because H acting on ket n is h cross chi n into n minus 1 ket n, n times n minus 1 ket n. This just pulls out a number. Recall that the number operator acting on ket n is simply n times ket n, and therefore, this is n minus 1, and again the number operator acts on ket n, pulls out an n. So, I can just write this as h cross chi n times n minus 1 ket n. So, all the photon number states are eigenstates of this Hamiltonian, and this is the eigenvalue n times n minus 1 essentially. So, let us look at what happens when n is 0. The eigenvalue is 0. Similarly, when n is 1, the eigenvalue is 0. Therefore, 0 is a doubly degenerate eigenvalue. And there are two states corresponding to this degeneracy, that is ket 0 and ket 1. So, both the 0 photon state and the 1 photon state are eigenstates of this Hamiltonian, the Kerr Hamiltonian, because they are eigenstates corresponding to a degenerate eigenvalue 0. All other eigenvalues are non-degenerate. For instance, if you look at n is equal to 2, that just gives me 2, then n equals 3 gives me 3 times 2, which is a 6, and so on. So, none of the other eigenvalues are degenerate, but the ground state is the 0 is degenerate. We have now looked at a large class of states of relevance to qubits quantum computation, of relevance to quantum optics, the single photon added coherent state, of relevance to the harmonic oscillator, because we looked at Fock states and we computed delta x, delta p, expectation values of other objects like xp, xp plus px and so on in these states. I would now like to move on and work out a problem in angular momentum, and this would be of relevance to particle physics. Suppose I have a Hamiltonian which commutes with the angular momentum operator j squared. In particular, j is spin, so it's not orbital angular momentum. So let me look at the spin angular momentum. So h s squared. Suppose I have a Hamiltonian which commutes with this, and the Hamiltonian commutes with Sx, Sy, Sz, and therefore with S plus. The spin eigenstates are denoted by Sm. Of course, Sz, Sm is mh cross S, comma m. These are the spin labels. Now, in this picture, I want to show that an object with a given spin has the same mass independent of whether it exists in the state m, the third component having a value m, or a value m plus 1 or m plus 2 or m minus 1. Independent of the value of m, provided the spin of the object is given to me, I want to show that the object has the same mass whether it exists in the state s comma m or s comma m plus 1 or s comma m minus 1. It is independent of m, provided the Hamiltonian commutes with S plus. In other words, it commutes with Sx, Sy, and of course Sz. The way I go about it is as follows. I know that this is true because H commutes with S plus, that is given to me. So, I expand this commutator out. So, this is what I have. But I know the action of S plus on S comma m. It raises the value of m by 1. So, let me put that in. You will recall that S plus acts on S comma m to give me root of S minus m into S plus m plus 1 h cross S comma m plus 1. M itself takes two S plus 1 values ranging from minus S to plus S in steps of 1. Similarly, S minus on S comma m gives me the following. I use this. In my problem, therefore, I started with this object and this implied H S plus on S comma m gives me H S comma m plus 1, pulling out this coefficient root of S minus m into S plus m plus 1 h cross. H cross is outside the square root. That is the first term, and this quantity is equal to S m plus 1 S plus H S m. But if S minus acting on S comma m gives me this, its dagger is this, and that is a real quantity. Therefore, I have the same coefficient. So, I use that here. So, S plus with an S comma m on this side of it, except that I have m plus 1 instead of m. So, I use this and I have it reduces m plus 1 to m. Notice that this coefficient is the same as that coefficient, that scores off, and I just have the same coefficients. Therefore, root of s minus m times s plus m plus 1 h cross s m plus 1 h s m plus 1, the expectation value of the Hamiltonian in the state s comma m plus 1 minus the expectation value of the Hamiltonian in the state s comma m is 0. M is not equal to s, and therefore this coefficient does not vanish. So it tells me a very important property, that the expectation value of the Hamiltonian in the state s comma m plus 1 is the same as the expectation value of the Hamiltonian in the state s comma m. So let me look at the spin doublet, for instance. What does this mean for the spin doublet? In the case of the spin doublet, I have s is half and m is half, and s is half with m minus half. So this boils down to the statement that half half h half half is equal to half minus half, half comma minus half, h half comma minus half. That is what it means. In other words, look at the Hamiltonian. The Hamiltonian has in general a kinetic energy plus a potential energy for particles of a certain mass. This would mean the kinetic energy of the particle and the rest mass of the particle, the rest mass energy of the particle. Let us go to the rest frame of the particle. Let us go to the rest frame of the electron, which is a spin half object, for instance, or the proton or the neutron. The statement is this: in the rest frame, this expectation value would correspond to the rest mass of the particle in question. So the rest mass of the electron in the spin up state equals the rest mass of the electron in the spin down state. Similarly, for protons and neutrons, the rest mass of the proton in the spin up state is the same as the rest mass of the proton in the spin down state. The manner in which I take care of this is by starting off with a Hamiltonian which commutes with s plus. Once this is given to me, it automatically follows that objects in a certain state of spin, in the sense that s is fixed but m has a definite value, objects in a state m, s comma m, would have the same rest mass as the state with s comma m plus 1 or m minus 1. In other words, in a spin multiplet, the same holds for a spin triplet, for instance. In a spin triplet, the rest mass of the object in the state 1 comma 1, in the state 1 comma 0 and the state 1 comma minus 1 would all be the same. So within a spin multiplet, the rest mass is the same. We discuss a certain particle in a certain state of spin, therefore, but it could exist in different states of m. Whatever may be the state of m, the particle has the same rest mass. That is guaranteed by the fact that h commutes with s plus. So I have worked out certain exercises for you using commutator algebras. Essentially, the algebra involved in the case of the harmonic oscillator, xp commutator is IH cross, equivalently A dagger commutator is 1, and the spin algebra, where I have used the fact that if I have a Hamiltonian which commutes with s plus, certain consequences follow.